Let's see. Last time we were talking about derivative, okay, and then we computed several derivatives, but the only thing that we know so far is a definition, which is the limit definition. And first of all, it's very tedious, it's long, and we only have dealt with very easy cases of functions to find the derivative, like polynomial functions. We have dealt with the square root function, but I think that's as far as we have gone. Like we haven't done anything else. What about a sine function, a cosine function, a logarithm, an exponential? How about rational function? How do you take derivative of those? You can use the definition, but you're gonna suffer a lot if you try to do the limit. So to be able to understand how to do that for those functions, let's talk about some rules. Okay, as I mentioned last time, there will be a bunch of little rules that you're gonna have depending on the function. That's a rule that you use to take the derivative. If you don't want to use the rules, be my guest. Then take the limit. But you're not gonna go too far with the limit. Okay, so that's why we're gonna spend some time learning the rules of derivative. Okay, so let's do the basic ones now, and then the following sections are going to be, okay, when the function gets more complicated, then there will be a special rule for that we need to discuss, and we need to learn how to use it, okay? And that's what's going to happen in this chapter, basically, just to make sure that you know how to find derivative of functions. Okay, so I guess let me remind you of the definition. So recall the derivative of f is given as follows. So let's see, who can tell me the definition? What is it? What's the definition of this?
F of A plus H.
Okay, f of x plus h.
Minus f of x over h.
Okay.
Limit as h approaches 0.
And then we need to take the limit as h approaches 0. So remember, this piece only without the limit, this is just a difference quotient, which stands for the slope of the second line from x to x plus h, okay? The line joining those 2 points. Only when you take the limit, that's when we talk about the tangent line, okay? That's how you specialize to that particular point. In this case, it's a function. The output of this is going to be all possible slopes for all possible tangent lines, okay? All right, so that's the definition. Don't forget this, because if you get a piecewise function, for example, and that point at which the function changes formula, there's no formula you can use. What do you use? Because the function changes formula around that point. The only way to analyze it is using the definition. Okay, so that limit, it has to be there. Okay, but anyways, let's write here some rules or some basic properties. And most of the basic properties that I'm going to write here, like 2 or 3 of the properties, they actually follow straight from the definition, just because we're doing a limit, okay, as you're about to see. So the first one is actually a very easy one, is what we call the constant rule. Basically, it says the following. So let C be a constant. So that is a fixed real number. Then what do you think is the derivative with respect of x of the constant? What do you think this is equal to?
0.
Why?
Because there's no slope.
Very good. If you think of this constant as a function, this is a number, whatever number you want, 20, 30, whatever. If you think of this as a function, this is a horizontal line, right? And what's the slope of the line? It's 0. Remember, for lines, derivative is just the slope of the line, okay? In the case of a line. So the point is that constants, they have derivative equal to 0. If you use the definition, because it's a constant, then f of x plus h is equal to c, because it's a constant, it's always the same thing. F of x is also c, so the top is already 0, okay? So 0 over h is just 0. So that should be clear. So proof of this, let me just say, since f of x equals c is a constant, then it has slope 0 everywhere. And that's enough. But if you want, you can also say, look, because it's a constant, when you find this definition, you take this limit. F is always the same thing regardless. So you get C minus C on top, and that's clearly equal to 0. Okay? Because no matter what you plug in, because F is a constant, I don't care what you're writing here, the output is always 0. That's what that means. Okay? All right, so moral of the story, derivative of a constant is 0. Let's see, let me write a couple of examples here. So find the derivative. And let's say that we have f of x equals 7, and f of x equals, say, pi squared. All right, what's the derivative of this function? Let's call this one g. So what's f prime?
0.
0. Good. What's g prime?
2 pi.
What do you mean by 2 pi? Why? What is pi? A constant. What's pi squared? It's a non-constant. It's like 9 point something, right? So it is also 0. I mean, this is a number. Everybody understand that this is a number? Pi squared is a number. All right. So moral of the story: if you find a number and you need to take the derivative, then that's 0. So that should be pretty straightforward. Questions? No? Okay. So second one. This one you're gonna be using. I don't want to say infinitely many times because we don't do anything infinitely many times, but close to it. Okay, this rule you're gonna be using this from now on almost every day when you are in a math class. Most of the times. Anyways, it's called the power rule. Okay, and basically this has to do with what's the derivative of x to some power. So before we actually write down the rule, let's do some examples to investigate, and hopefully you're gonna see the pattern. Okay, so find f prime, and then let's do f of x equals, let's say, square. Then let's do g of x equals x cubed. Then let's do h of x equals square root of x. And we already have done the derivative of these functions, okay? I just want to do it again, and then hopefully you will see a pattern, and hopefully you can tell me what the power rule says. All right, so let's do this. So for the first one, again, remember, all we know right now is just the definition, so that's what we need to do. Okay, so f prime, this is for number 1, that's the limit as h approaches 0 of f of x plus h minus f of x over h. Remember, just plug in. So we get x plus h squared minus x squared over h. Expand this square. So x squared plus 2xh plus h squared. Then the x squares cancel out. And then hopefully you see here that in the terms that survive on top, they both have an h. Okay? So we can factor out that h and cancel it with this. We have done this many times. So this now becomes limit. As to simplifying, what remains in the top is a 2x plus h. Everybody see this? There's this h and one of the h's here, they cancel with this one. Okay? All right, and then after we did the limit, what's the answer here? What's the answer? 2x. So moral of the story, the derivative with respect of x of the function x squared equals 2x. You okay with this? All right, let's look at the next one. So I want to do 1, 2, and 3, and then we're gonna look at the results once again, and then hopefully a certain pattern will emerge. Okay, so we're dealing with x cubed now. So that's g of x plus h minus g of x over h. So limit as h approaches 0, x plus h cubed minus x cubed over h. Expanding the cube, we're gonna get x cubed plus 3x squared h plus 3x h squared plus h cubed, then minus x cubed all over h. These guys cancel, and once again, all the terms that survive on top, notice that everybody has an h. So once again, I can factor out that h and simplify with this one. So after simplifying, what do we obtain? So we have 3x squared plus 3xh plus h squared. That's what we get after we factor the h in the top and simplify with this one. And when you take the limit, everything that has an h is gone, becomes 0. So this equals 3x squared. Yes? You okay with this? So the moral of the story is that the derivative with respect of x of the x cubed function equals 3 times x squared. So the derivative of x squared is 2 times x. The derivative of x cubed is 3 times x squared. Okay. Let's take a look at the last example. So function was square root of x. Anybody remember the derivative of square root of x? Told you last time, memorize it because you're going to be doing that one a lot. Anybody remember?
1 over square root. Or 3.
1 over 2 square root of x. So let's do it. Since you haven't memorized it yet, then let's do it. But this is going to show up a lot, so it's good to remember. Okay? Anyway, if you don't remember, then you can use the power rule that we are about to do now. Okay, so this will be square root of x plus h minus square root of x over h. So what's the technique in a situation like this? What do we need to do? Multiply top and bottom by the conjugate. Good. Okay. And when we do this on top, remember, we get a difference of squares. So that will be limit as h approaches 0. Then the first term square is just x plus h. The second term is just x. And then this is what we get. The x's on top cancel out. And then this h over here cancel with this one. Okay? So we are left with 1 over square root of x plus h plus square root of x. Once again, these x's cancel out, and then the h on top cancel with this one. That's why there's a 1 left over. And after you take the limit, because h approaches 0, we put 0 here, and you get a square root of x plus square root of x. So we get 1 over 2 square root of x. Okay? So the derivative with respect of x, the square root function, is 1 over 2 square root of x. Are you okay with this? I'm gonna rewrite this a little bit so that I want this to match somewhat the pattern that we are seeing with the previous 2 examples, okay? So I'm gonna rewrite this a little bit. So square root of x, I'm gonna write it as x to the 1/2, okay? And then this x to the 1/2, I can bring it to the top. How? X to the negative 1. So we can write this as 1/2 times x to the negative 1. Does everybody understand this? Yes? Do you know what rule of exponents did I just use? Yes or no? I'm not sure if some of you know. So let's see. Basically, just use this property. If you have a to the negative k, this is 1 over a to the k. So basically, this means when you have an exponential expression, you can always write in the denominator by changing the sign of the exponent. Okay? But also the other way around. If you have something in the denominator, you can always bring it to the top by changing the sign. So negative k and k, they have opposite sign. Okay? if you have something negative on top, you can bring it to the bottom and make it positive, or the other way around. You have something down here, if it's positive, you can bring it to the top and make it negative. But also, if this guy was negative, now negative k would be positive. Do you understand this? The k could be positive or negative, I don't care. This is just saying that this exponent and this one, they have different sign. Okay? That's all the same. And that's basically the rule that I use. I wanted to bring this guy to the top because it's positive a half. I can do it by writing negative a half. Okay? All right. So let's see. Let me summarize this. So we have derivative with respect of x of x squared is 2x. Derivative with respect of x of x cubed was 3x squared. And then finally, okay, so if you don't mind, instead of square root of x, I'm going to write it as x to the 1/2. Because the pattern, hopefully here inside the brackets, you see it's x to some power, right? So square root of x, let me write as x to some power. So we can write as x to the 1/2. And in this case, it turned out to be 1/2 x to a negative 1/2. We okay with this? All right. So I know most of you already know, but anyways, I'm going to ask, do you see a pattern in here? Let's see, what pattern do you see?
The exponents changed.
Okay. How did they change?
You brought the exponent down and then the old one just subtract by 1.
Okay, does everybody see what your classmate just said? So, for example, here we have an exponent of 2, and it turns out that that exponent came down here, and then what's the exponent that we have over here? So, let's specify that. We have an exponent of 1, which turns out, in this case, that 1 we can write it as 2 minus 1. Yes? So, what your classmate said is, oh, this exponent came down, and then we subtracted 1. Do you see that? Let's see, is that happening in the next one? Does this fit the same pattern? So exponent came down, and then we subtracted 1 because 2 equals 3 minus 1. How about the next one? Does it fit the same pattern? So the exponent was 1/2. Okay, yes, it came down. Now, is negative 1/2 the same thing as 1/2 minus 1? Is it the same thing? Yes or no?
Yeah.
Yes, it is, right? So 1/2 minus 1 is negative 1/2. So remember, this is the same. 1 is the same thing as 2 over 2. So 1 minus 2 is negative 1, right? We're about to write, but we need to wait a little bit more. We need to wait until we know about implicit differentiation. Right now, with the knowledge that we have, we could argue when you have x to some integer, like a positive number, then we can use binomial theorem to be able to prove the rule. But then when you have rational numbers like this, or even irrational numbers like x to the pi, the rule also applies. Okay? But to be able to argue and see why that's the case in any situation for any exponent, we need to weigh a couple of sections. Once we discuss implicit differentiation, we're going to come back and we're going to discuss this idea. There's a technique called logarithmic differentiation that is done in the section of implicit differentiation that will allow you to justify this completely. Anyways, the pattern here that we see is that if you take the derivative of x to some power, let's say r is, I don't want to say n because typically n represents an integer, but it doesn't have to be. So if you have x to some power, then what should be the rule here, according to what we're seeing?
Rx to the r minus 1.
Good. So bring the power down, subtract 1. Okay? It's very simple. And now we don't have to suffer these painful expansions anymore. Okay? And mind if you have x to the 10. You don't want to sit there and do x plus h to the 10 power. Okay? Moral of the story is that most of all those terms that we show up, they all will have an h anyways. So when you take the limit, the h is gone. Okay? That's all right, so this is the power rule. Okay? So power rule. It says for any real number r, for any real number r. And keep in mind that here r I'm saying any real number, so it could be positive, it could be negative, it could be an integer, it could be a fraction, whatever, a real number. Okay? The examples that we did, they were positive numbers, but they don't have to be. They could be negative numbers. Do you understand this? Okay. So for any real number r, we have that the derivative with respect of x to the r is r times x to the r minus 1. And this is true for any real number. Okay. Okay. Questions about this rule? All right. So let's do a couple of examples. Actually, I mean, let's write down a particular case, but it's good to remember this. So remark, in particular, we have a small derivative here. What is this? Equal to?
0. 1 over x.
1.
Okay, so you have told me different things. Which one is it? One of the answers was correct. Which one is it?
I think it's 1.
It's 1. Very good. A different way to think about it. This is a line. This is the line y equal x. Derivative is a slope, right? For lines, derivative is the same thing as a slope. What's the slope of this line? 1. Or you can use the power rule because this is the same thing as x to the 1, right? Bring the 1 down and then you have 1 minus 1. So what's x to the 0? It's 1. So 1 times 1 is 1. Do you understand this? But you don't want to use power rule on something like this. Moral of the story, the derivative of x is just 1. Do you understand this? Okay. So again, this one will pop up many times, so it's good to know. So examples, find the derivative. Let's see, let's do f of x equals x to the 5. And let's do f of x equals 1 over x. And let's do g of x equals cube root of x. And h of x equals 1 over x cubed. Okay, so give it a try with these 4 functions. Actually, no. Yes and no. I'm gonna give you like 2 minutes, so try to do it, then we do it together, then I'm gonna give another one in which we have the equation of a tangent line, and once you do that, then I take attendance. Because I wanna see if you can do the tangent line at this point. Okay, who has an answer for number 1? What's the derivative? Yes?
X to the power of 4.
Very good. Everybody okay with this? Yes? Okay, good. All right, how about number 2? How do we do this? So, if you notice, in the case of square root, if you wanted to use this rule, what do you need to do first? Because after all, this rule is about x to some power. As long as you can express your function as x to some power, then you can use the rule, okay? So sometimes the function, the way it's given to you, it doesn't look like x to some power. The question is, can you write it in that form? If you can do something to write as x to some power, then you are in business for using the power rule. So in this case, if you want to do the derivative of the square root of x, this is not a good form, right? So instead, we can use the fact that this is the same thing as x to the 1/2. And the moment that you recognize that it can be written as x to the 1/2, then you can activate the rule. Do you understand this? So if the function is now already in the form x to some power, and you want to take the derivative, you need to wonder yourself, can I write it as x to some power? Sometimes you cannot, and then you have to do something else. Okay? But in situations you can, and then you should use it. So 1 over x. Does it look like x to some power? No. Now, can you write it as x to some power? What is it?
X to negative 1.
We can write it as x to a negative 1. That's exactly the property that we were mentioning earlier, right? So this can be written as x to a negative 1. Does everybody understand this? Now it has the form x to some power, so we are in business. Okay, so what would be the derivative in this case?
Negative x to the negative 2.
Negative x to a negative 2. Everybody understand this? Now, typically, we don't like to have negative exponents, so then we should rewrite this. And what do we get?
Negative 1 over
Negative 1 over
x squared.
x squared. So the x to a negative 2, we bring it down as an x squared. Questions? All right, how about number 3? So let's see, first, do we need to do something to this? Do we need to modify it in some way? How? How do we write it?
X to the 1/3.
X to the 1 over 3, right? Now we are in business. Yes? Okay, so what is it?
I got 1 over 6 times the square root of x.
1 over 6. What is the 1 over 6? Why 1 over 6? All right, let's see. What do we need to do?
That's the 1, right?
We bring down the exponents, right? So 1 over 3 times x to the 1 over 3 minus 1. Everybody understand this? Just bring down the exponent and then subtract 1. Now let's do 1 over 3 minus 1 over 3. What is this?
Negative 2 over 3.
That's negative 2/3, right? Remember, 1 is 3 over 3. So you can write this as 1 over 3 times x to a negative 2 over 3. Are we good? And then we can bring this down as 3. So 1 over 3 times x to the 2/3. You stop there, that's fine. If you want to write it as a radical, how do you write this as a square root? So not square root. How do you write this as a radical? This is the cube root of x squared. Yes? So if you want, you can write this as 1 over 3, the cube root of x squared. And then maybe you want to rationalize, but at this point we'll just stop here. Okay? I'm not gonna be doing all those steps unless the question asks you to do so. So this one right here is good enough. Okay? All right. Questions? So where was the 6 coming from? I'm confused.
I missed it.
But remember, it's very simple. Just take this guy down and subtract 1. That's all you have to do. Yes? Okay. This would have been a nightmare if we wanted to use this by the definition, by the way. If we wanted to do this by the definition, it would be a nightmare. Because the conjugate is not going to work here because this is not a square root. This is a cube root. Okay, so it would have been way more complicated. But anyways, this rule in general works, and you will learn why later. Okay, once we do implicit differentiation. Okay, and then how about the last one? Do we need to modify it? How do we write it? It's to a negative 3. As I understand why we're writing it like this. If you want to use the rule, you need to have x to some power. Otherwise, you cannot use the rule. Okay? All right? So what is it? Good. And how do we rewrite this? No, the negative 3 stays there. Remember, the only thing that comes down is whatever has a power. Do you understand? So this negative 3 is not being affected by this negative 4. So this means negative 3 times x to the negative 4. So This guy comes down, but this one stays there. Is this clear? Okay. So this is -3 over x to the 4. Questions? Do you understand how to use this rule? Okay, I'll give you one more. So now let's do one about finding equation of the tangent line. So find the equation of tangent line of the function f of x equals 1 over the 4 root of x cubed at x equals 1. So I only have to give you the x. If you want to know the actual point, just plug in 1 here, which happens to be 1 also. So I guess the point on the graph is a 0.11. Okay? I just have to tell you this. So find the equation of a tangent line. So remember, your answer has to have this format: y equals mx plus b. Okay? So this is the answer that I'm expecting. A line. You have to give me the equation of a line. Okay, so work on it. Let me take attendance. Anybody has an answer? Give you 1 more minute. You should really try to do this on your own. You will be doing these kind of things in the exam. I mean, this is the reason why we're talking about derivative at this point, so we can answer a question like this. So we can find tangent lines.
I got y equals 2.
It shouldn't be. Because if you tell me y equals 2, that's a horizontal line. So you're telling me that the slope is 0. And the slope is not 0 at this point. Let's see, has anybody made any progress? Who can tell me what needs to be done? I mean, don't tell me the answer, just tell me what needs to be done.
Change it to a power.
Why?
Choose a power.
Why?
Find the derivative.
Why? I mean, the question doesn't say to find the derivative, so I'm wondering why you want to do those things. I'm not saying it's wrong. Yes. Okay. Why?
Because I needed to make the equation.
I mean, why are you shy about this? That's the way that you have to think about this. What am I asking you to do? To find the equation of a line. Yes, that's a question. Find the equation of a line. What line? Is a tangent line. What do you need to find the equation of a line? Is that it? You need a slope and a point. So your job is to find the slope, to find the point, and then once you have that data, then you go ahead and you find the equation. So let's see, before we even go further, do you know how to do this? If I tell you find the equation of a line with slope 3 and pass it to the point 4,7, do you know how to answer that question? If I give you slope and a point, do you know how to find the equation of that line? Yes? I mean, if you don't know, I mean, we will do it here, but that's the first thing. You need, once I give you a slope and a point, you have to be able to find the equation and then you're done. Now, the question is, how do we find these ingredients? How do you find the slope? How do you find the point? So let's see, the point. Do we know the point? What's the point? 1, 1. So everybody see this? X is 1. How do you find the y? Plug it in. You get 1 as well. So we know the point. That's not an issue. The question is the slope. Now, how do we find the slope? You see, all of this thought process has to go in your head. You don't have to write it, but it has to go in your head. So how do you find the slope of this line?
Use the power rule.
So you find the derivative of the function because it's a tangent line. Now, to find the derivative of the function, you look at the function. It looks like we can use a power rule. But before we do that, we need to play with the function a little bit. Yes? And then you activate the process. If you don't have this thought process in your head, you're just working mechanically. Because of course, we're talking about derivative, then you're expected to take derivative at some point. But if out of context I give you this question, you need to know what to do. Okay? okay? Let's say that we're talking about cars, and all of a sudden I tell you, by the way, find the equation of the tangent line. You need to know what needs to be done, okay? So, all right, so then, and it's always good to write it out. So what do we need for this problem? We need a point, and we need the slope. Once we answer these two questions, then we're good to go. So what's the point? Do we have it? So a point is 1, 1, so not a problem. The slope, let's call it m. Do we have the slope? We don't have it yet, right? How do we find it? We take the derivative of the function, and is that it? Remember, the derivative of a function is a function. The slope is supposed to be a number. How do you obtain this number?
By plugging in x at that point.
Which is 1. So you need to find f prime of 1. Do you understand this?
Yes.
Right? Because this is the slope of that tangent line that we're looking for. Okay? So now, since we already have the point, we just need to figure out the slope. Now this is telling you what to do. Find the derivative and then plug in 1. Okay? So to find this, before we even find m, we need to find f prime. So let's do it. But we need to play with the function a little bit. So how can we write this? As x to some power? Everybody understand this? So the reason why I left space is because there is an in-between little step here. This radical, we can write it as x to the 3/4. Remember, the index of the radical goes in the denominator. Okay? And whatever little power you have in here, it goes in the top of the fraction. And now we bring it to a top, the negative exponent. So now we are ready to find f prime. What's f prime? Let's see, using the rule. Don't give me the final answer, just use the rule. What is it? Negative 3/4 x.
Negative 3/4 minus 1.
Negative 3/4 minus 1. Yes? And if you want, you can simplify this. So let me just do it for practice. So remember, 1 is 4/4. You can write it as 4/4. So negative 3 minus 4 is negative 7. Right? So that would be negative 7/4. If the question was find the derivative, then you should do an extra step here, which is bring this guy down and so on. But remember, I don't care about this. I care about the value of this when x is 1. So don't waste time, because if you start simplifying things, you could even make a mistake. And then you get the wrong formula, and then when you plug in, you get the wrong number. So right here, I'm going to stop. I'm going to plug in my 1. I don't care about this, because this will become 1 anyways. 1 to whatever power is just 1. Yes? So what's the slope? Negative 3/4. So from here, we can immediately find our m, which is f prime of 1, which happens to be negative 3/4. If you plug in 1 here, this guy is gone, becomes 1. Do you understand this? So we can put here now a number, negative 3/4. Let's see, I'm going to give you a minute. You have the point, you have the slope. Find the equation. Okay, you tell me your answer. Let me allow them to do it. He wanted to say. Yes. Okay, so what do you get?
Negative 3/4x plus 7/4.
Okay, so let me write it here. So then that means that with this data we get negative 3/4x
Plus 7/4.
plus 7/4. Is everybody getting the same thing? Okay, so we're gonna do it. But let's see, there are two ways to do this. As I talked about this the first day. We can use something called the point slope formula. It's a formula that if you know the 1 point in the slope, just put in the formula and you get your equation. Okay? Just for y and the sun. Or you can do it another way by, since you already know the slope, you already have a predefined form for the line. So you already know that this looks like negative 3 over 4x plus something, or maybe minus something, depending. We need to figure out what that something is, the b part, the y-intercept. And then use the point information to find the y-intercept. Which one of the two do you want me to do? Or which one do you feel more comfortable with? But I should say less comfortable with, so you see. Do you want me to use the Points-Law formula? Points-Law? Okay, good. So, do that. So once you have the point and the slope, then we're gonna use the Points-Law formula. And the Points-Law formula is, so you don't forget, is basically, it's very easy. Do you remember the slope formula? What's the slope formula? The slope formula. How do you find the slope of a line? If you know 2 points, how do you find the slope? Y2 minus Y1 or x2 minus x1? Everybody knows this, right? Okay, so instead of x2, y2, let's call this xy. So this point, this one means any point on the line, and then this is a fixed point on the line, right? All I did was erase it. We didn't do anything hard. Okay, now just bring this over here. So if you multiply x minus x1, you bring it to the other side, then I'm gonna switch things around. You will get y minus y1 equals m times x minus x1. This is the Points-Law formula. You put the slope here and 1 point, and so for y. Do you understand this? So, if you forget, if you want to use this and you forget, just remember, write down your slope formula, and then it comes from there. So, y minus y1 equals m times x minus x1. All right, so let's put a point. What's the point? 1, 1, right? So remember, let me put here x1, y1. This is the point 1, 1. And our slope is, what's the slope? Negative 3 over 4. Okay, so I'll just put that data. So y minus 1 equals negative 3 over 4 times x minus 1. And typically we give the answer in the form, in the slope intercept form, mx plus b. So now you just solve for y. So that's negative 3 over 4x plus 3 over 4. And then we just add 1 to both sides. So we get y equals negative 3 over 4x. And then 3 over 4 plus 1, this is 4 over 4. And then that would be 3 plus 4 is 7. 7 over 4. Okay. Questions? Do you understand how to do this? Okay. So by the way, I want you to understand that, for example, the last 2 examples that we did, actually the last 3 examples. So 3, 4, 5, they would have been very difficult if you wanted to use the definition. Okay? If you didn't know the power rule, to answer a question like this, you will be there a while trying to figure out that little. Okay? So it's important to know these little things. Okay, any questions on the power rule? So we have the constant rule, we have the power rule, and there's another one which is the constant multiple rule. And that one basically says the same way that we can take constants out of a limit. We can factor out a constant out of a limit. We can also factor out a constant out of a derivative. Okay? So let me write that down. So number 3, you don't really need to know the names. You just need to know the rule and use it. Okay? But they have names, so give you the names. It's the constant multiple rule. And like the name suggests, that's when you have a function that's multiplied by a constant. Okay? And basically, the rule is, so theorem, if f is differentiable at x equal a, so if f, let me say if f is differentiable on its domain, okay, and k is any real number, then there is a new function that we can form, which is k times f. So remember, every time that you have a function, you can get a bunch of other functions from it. One of those is by multiplying it by a constant. You can also raise it to the power and do many things to whatever formula f is. So this is a new function, and because f is differentiable, this new function is also differentiable. Okay? Is also differentiable. Remember, differentiable means the derivative exists. You can take the derivative. Okay? And moreover, we have a formula for this. So the derivative with respect of x of k times f is just k times derivative of f. Okay? Which just means it's k times f prime. So moral of the story, if you take the derivative of a constant times a function, you can just take the constant now. Take the derivative of the function and then multiply your result by that constant. Okay? So proof is pretty easy, it's just using the definition. Okay, so if you want to take the derivative, so whenever the proof is simple, I'm going to show it to you because why not? So if you want to take the derivative of a constant times a function, remember, if you're arguing this, the only thing that we have at disposal is the definition, so just write it. So that will be the limit as h approaches 0. Now I need to plug in x plus h in here, but the point is that the x plus h is plugging inside, then minus k times f of x, that's the function, over h. So you can think of this as a function g. So you see what I'm doing here. If I were to call this a new function, let's call it g. This part here is the g of x plus h, and this part here is the g of x. Okay? All right, so now what can we do? Well, I can factor out k on top. And we can write this as k times f of x plus h minus f of x over h. So basically all I did was I factored out the k on top and then I wrote it as k times this fraction. Okay? I don't know anything. Now, as you know, the limit of a product is a product of the limits, or in other words, we can take constants out of the limit as long as the other limit exists. But because we said that f is differentiable, that's what it means for this limit to exist when h approaches 0, right? It equals the derivative. So by using the properties of limits, we can take the k out. And now the limit that we have here is precisely what we mean by derivative of f. So derivative of k times f is k times derivative of f. Okay? So it's just using the properties of limits. All right. So let's see this in action. Again, just put the constant up. Okay. So examples. Find the derivative. Let's see, let's do f of x equals 6x cubed. Let's do y equals -1 over 2 cube root of x squared. Let's do g of x equals 2 over 3 times square root of x. And do y equals 5 over 3 times x to the 9. So here we have 4 functions. Go ahead and find the derivative. Let's see, I'm gonna do, okay, so I'm gonna do number 4, and then I'm gonna let you do 1, 2, and 3, okay? Just to show you how to use this. I could do 1, but then this is like the easy case. So I'm gonna leave it to you. Let me do this one. It's also kind of easy, but it requires a little extra step. Okay, so solution, I'm gonna do 4 first. So for number 4, we have a function y equals 5 over 3x to the 9. So hopefully you see that this is some sort of modification of the function 1 over x to the 9. Yes? In fact, you can think of this as what? How can you write this as, there are numbers and then there is a function 1 over x to the 9. Does everybody see the function 1 over x to the 9 here? So we can write this as a number times the function 1 over x to the 9. What is that number? 5 over 3. Yes? So we can think of this as 5 over 3 times 1 over x to the 9. Does everybody see this? So you see that this is a constant times a function, so you may want to use the constant multiple rule. But then the question is, at some point you will have to deal with the derivative of 1 over x to the 9. And to deal with this derivative, can we leave it like this, or do we need to write it in a different way? We should write it how? X to the negative 9. So that's the reason why I'm going to rewrite this as 5 over 3 times x to the negative 9. Okay? So now we have the equation ready. Because our function now has a form constant times a function, and this function we know how to take the derivative. Okay? So let's do it. So dy dx, or you can write y prime, whatever you want. Okay? This is Leibniz notation. So dy dx is the same thing as y prime. Okay? Okay, so that would be the derivative of 5 over 3 times x to the negative 9, because that's what y is, right? 5 over 3 times x to the negative 9. And then what the constant multiple rule says is that this is a constant, therefore I can take it out. So this is the same thing as 5 over 3 times whatever the derivative of x to the negative 9 is. Do you understand this? Now let's take the derivative of x to the 9. What's the derivative of x to the 9? Good. So then this becomes 5 over 3 times negative 9 x to a negative 10. And now just simplify. So for example, this 3 cancel with the 9, giving you a 3 here. So 5 times negative 3 is negative 15, and then the x to a negative 10, and I put it in the bottom. Questions? Any questions? Okay. Now apply this idea to number 1. You don't have to modify anything in number 1. Just use the property immediately. Yes. But then for 2 and 3, you have to do some pre-work, right? Like you have to prepare the problem.
So number 1 is at a 6 or a B? Number 1.
Okay, so let's give a couple of seconds and then you go for it. So for 2 and 3, you have to do some preparation like what we did for number 4, okay? So basically we're combining here 2 rules, right? So this problem is combine the constant multiple rule together with the power rule. So what do you get for number 1?
18x squared.
Oh,
3bx squared.
which one? What is it?
bx squared.
Okay, that's a 6. Okay, sorry.
Oh, a 6? I couldn't
Yeah.
tell.
Yeah. Okay, so that's a 6.
This one's a b. I'm an idiot.
Okay, if it was a B, what was your answer?
3bx squared.
Okay, so now I'm telling you B is a 6. So what will be the answer?
Anyone's gonna do a calculator.
No. What's 6 times 3?
18.
Good. So 18x squared.
Yes.
Okay. So now you know my 6 and B's are almost the same. So unless I tell you that there is a variable, if you think there is a B, it's a 6. Okay? Unless I tell you.
I got so confused with that.
I mean, I'm not going to put a random letter there if I don't tell you what it is. Unless I tell you, let B be a constant. Now you know a B is constant. But otherwise, it's a 6. Okay, good. Everybody agree that number 1 is 18 squared? Good. So for number one, we have f. So f of x was 6x cubed. You know, when it's something like this, you don't go through all the process, right? All of that, dx, etc. You know, we can just easily say that f prime is just 6 times 3x squared, which is 18x squared. And if you write 18x squared, that's fine, okay? All right. So let's see, number 2 was, the function was, so let's see, who can tell me what would be the friendly form of this before we even take the derivative? Yes?
Negative, the friendly form would be negative 1 over 2x to the 2 over 3.
Where? In the bottom or so?
Yeah, the bottom, x to the 2 over 3.
Okay, so down here.
Yeah.
Is that it? You should do something else. Are you ready to take derivative like this? Yeah, but when you do the derivative, what do you do?
I put a negative.
X to a negative 2 over 3. So that's what I mean. Like, prepare your function. Otherwise, when you take derivative, you need to stop and prepare again. So just, you know, prepare everything that you need. So negative 1/2 x to a negative 2 over 3. I mean, you do what you want. I'm just telling you. Anyways, if you don't do it now, we need to do it later, right? Everybody understand this? Okay. So, what's the derivative?
1 over 3 times x root 3 to the 5.
Okay, so let's do it slowly. So that would be, so that's the final answer. So tell me your final answer.
It was 1 over 3 times x root 3. Well, x was on the bottom.
Okay, so
Times x root 3 to the 5.
so cube root of x, like that, and then x to the 5. Okay, all right. So we see. There are some stuff that needs to happen before we get there. Yeah, you don't go from there to there in one shot. So what do we do? So negative 1/2 is a constant, yes. So we just ignore it in the sense that we just keep it there. It doesn't do anything. It will do something later. So that will be negative 1/2 times, and then we focus on taking the derivative of this part right here. Yes. So what's the derivative of that? Negative 2 over 3 times x
to the negative 5 over 3.
to the negative 5 over 3. Good. Because that would be negative 2 over 3 minus 1, which is negative 5 over 3. Okay, so now here, now it's just simplifying. So negative times negative is a positive, the 2's cancel out, and that's where the 1 over 3 comes from, right? So these 2's cancel out, negative times negative is a positive. Here. So then we get that this equals 1 over 3 times x to the negative 5 over 3, but then we can bring that down as 1 over 3 times x to the 5 over 3. And then you can write it as a radical if you like, as the cube root of x to the 5th. And at this point you can just keep it like that. So you write this, and then you want to be picky, then okay, now rationalize, and then it's never ending. I mean, it ends, but so I would typically just stop here. If you are asked to give the answer as a radical, you need to know, of course, how to write it as a radical. Okay, that should be okay. All right. Does everybody understand why the answer is positive and not negative? The constant was negative, and then when you bring down the exponent, that's another negative, and they cancel each other. Okay? Be careful there. Questions on number 2? All right. And how about number 3? We have the function g. It was 2 over 3 square root of x. So what is the derivative? Let's see, anybody remembers the derivative of square root? 1 over 2 square root of x, okay? If you don't remember, what you need to do is write it as x to the 1/2 and then use power rule, okay? But that function is gonna show up many times, so it's good if you know it, that way you can work fast. Okay, so what's g prime?
One over 3 times square root of x.
So 1 over 3 times square root of x. Good. So how do we get there? Well, this is 2 over 3, the constant stays there, and then times the derivative of square root, which is 1 over 2 square root of x. Okay? The 2's cancel out, and then you get this. Any question? Yes?
Can you also write it as 1 over 3 times x to the 1/2? Or does it like matter?
Yeah, it's just that, if you have x to the 1/2, that's square root, but it doesn't matter. You can write here x to the 1/2. If I see another weird power, I mean, any other fraction, I would just leave it like that. But if it's 1/2, I would rather write the square root, but it doesn't matter, just a matter of notation. Okay, questions? Do you understand these properties? Okay, good. And now, this is fine, but what about, if you have x cubed plus the fifth root of x? How do you take the derivative of something like this? So we know how to take the derivative of x cubed. We know how to take the derivative of the fifth root of x. How do we take the derivative of the sum? So we have a rule for this. And the point is that, we have it for limits, right? The limit of the sum is the sum of the limits. The limit of the difference is the difference of the limits. Those properties, they carry over to derivatives, because remember, the derivative is a limit. So most of the things that you know about limits, you can kind of translate them to derivatives. Like we enjoy the constant multiple rule, that came from limits directly. Similarly, the fact that you can add the two limits, that will mean that when you take the derivative of the sum, that's the same as the sum of the derivative. And the derivative of the difference is the difference of the derivative. Okay? So now we can combine a bunch of functions. It will look very complicated expression, but if it's just made out of little functions that you know how to take derivative, then find the derivative of that big function is okay. All right? So that's the next one. The sum and difference rules. And what number are we? In number 4. So sum difference rule, and basically, it's a theorem, and it says let f and g be two differentiable functions. In other words, you can't take derivative. Derivative exists. Be two differentiable functions, then the derivative of the sum is the sum of the derivatives. That's one item. The second item is derivative of the difference is the difference of the derivative. Okay? So shorthand notation would be, shorthand will be, you have f plus or minus g. The derivative of this is f prime plus or minus g prime. Okay? So derivative of the sum is the sum of the derivative. Derivative of the difference is the difference of the derivative. Okay? Right. Let's see. I'm gonna justify the sum, and then I'm gonna leave the difference for you as a homework. Okay? So proof. So I would do the sum which is I want to show that the derivative of the sum equals the sum of the derivative. Okay, that's what I want to show. All right, so the derivative of f plus g. Now remember, when we say f of x plus g of x, that's really a function, and the way that we write this is as f plus g of x. That's the formal notation. Okay. And the way that we evaluate this when you plug in a number is we plug in that number into f and we plug in the same number into g and then we add the results. That's how we define additional functions, okay? Which is what this is telling you. But I want to write like this because I want to have this form. So you can think of this as being a new function, let's call it h. So you have two functions, f and g, you add them, you get a new function. Let's call it h. So that derivative is limit as h approaches 0 of h of x plus h. Let's call it capital H. That h is different than the other h. Minus h of x or h. Okay, now let's see what's capital H of x plus h. That's just plugging in x plus h into this function, which means plugging into here. Okay. So that's going to be limit as h approaches 0 of f of x plus h plus g of f plus h minus the function h, which is f plus g all over h. Okay, so now I'm going to distribute this negative, so we get negative f minus g, and I'm going to group things together. Okay, I'm going to rearrange terms in the top in a convenient way. So I have my f of x plus h, then minus f of x. I'm going to put those guys together, and plus, and then I'm going to have g of x plus h minus g of x all over h. Again, all that I did was I distributed this negative, and then I just shuffle things in the top. You can do that, okay? When you have addition, subtraction, you can move things around. So this is the first term, f of x plus h, and then minus f of x, right here in red. Then g of x plus h minus g of x, right here in blue. Everybody okay with this? Now, I'm going to split these as two fractions. We get limit as h approaches 0 of f of x plus h minus f of x over h plus g of x plus h minus g of x over h. All of this is happening inside the limit. And as you know, the limit of a sum is the sum of the limits. Here is where we use the property of limits, right? Limit of the sum is the sum of the limits. Write it down. So this is now as long as each limit exists. But they both exist because remember we said the functions were differentiable. So as the first limit plus second limit. So what's the first limit equal to? The red limit. What is this? This is exactly what we mean by f prime of x. I mean, that's the definition. Plus, and what is the second limit? That's g prime of x. So moral of the story, we started with derivative of the sum. So I'm gonna write it as prime notation. So derivative of the sum is the sum of the derivative. Okay. Now notice that the same argument works if instead of a plus we had a minus here. You just have to adjust it a little bit because if we have a minus here, that means there's a minus here and there's a minus here. Okay. Then you have to modify the argument in such a way that then there should be, once you do all your rearrangements, instead of a plus, you're going to end up with a minus here. Okay? And then you do the same thing. I'm going to leave that to you as a homework. So, homework. Prove the other, which is that derivative of f minus g is f prime minus g prime. But the argument is done in a very similar way. Okay. Okay, so let me put examples, because now this opens up a whole world of possibilities for all the functions that we can take derivative. For example, you can now find derivative of any polynomial. Okay, because polynomials are just a combination of addition and subtraction of power functions times a constant. You know how to take derivative of power function. You know how to take derivative of a constant times a power function, and now you know that you can take derivative of sum and differences. So any polynomial now, you can find derivative. Find derivative. You know, the good things about these rules is that we use the limit, but only once to get the rule, and then that's it. You don't have to use this limit anymore. You can just use the properties. Okay, so here you have three functions. By the way, attempting to do this using the definition as we were doing last class would be a nightmare. Okay, and now this is streamlined very easily using the properties. So go ahead and try these derivatives. I'll give you 5 minutes. So the first one is x cubed minus 4x plus 5. So by the way, I wrote the rule for two functions, for the sum of two functions, but as you know, if you add three functions, it's the same idea, it's just that you use the rule twice. So what I mean is, let's say that you want to do now f plus g plus h. You want to take the derivative, you know, technically you could say, okay, this is f plus, and then you can call g plus h a new function, so apply the rule once, okay, and then you apply it again. Derivative of g plus h, that's just g prime plus h prime. So moral of the story, if you add three functions, the derivative of this, the sum of the three functions is the sum of the three derivatives. And if you have 20 functions, it's the sum of the 20 derivatives. Okay? Just applying the same rule over and over again. Same thing with the difference. So for the first one, this is just derivative of the first minus derivative of the second plus derivative of the last one. Okay? And same thing for the others. In C, be careful. You have to do some modifications first. Okay, anybody has an answer for So for the first one, what's f prime?
3x squared minus 4.
So 3x squared minus 4. Very good. Did everybody get the same thing? So let's see. Let's do this. Let's put a couple of steps. So normally at some point, when you see this, then you can immediately write this in one shot. Okay. But I'm gonna write all the steps so you can see what just happened here. So if you want to find the derivative of f, this means that we're taking the derivative of all of this, right? Yes? Now we use the property. This is a combination of addition and subtraction of three functions. So the property that we just discussed allows to write minus the derivative of 4x plus derivative of 5. That's typically what happens, but typically we do this step in our mind. Like we see the function, we say, okay, that's the derivative of this guy minus derivative of this plus derivative of this. That happens in your mind. You just write it down now so you can see what's going on. Now, this is like the little problems that we have been doing since the beginning today, right? So, what's the derivative of x cubed? 3x squared minus, what's the derivative of 4x? So, let's see, I'm gonna write 4 times 1, right? 4 times the derivative of x, which is 1. And plus, what's the derivative of 5? 0, remember, constant rule. And when you put all this together, you get your 3x squared minus 4. Are we okay with this? Right? Good. Okay, so the next one, B, which is g of x equals negative x to the 4 over 2 plus 3x cubed minus 2x. So let's see, at this point, there is no need to write, that first step that I did all the time. We just go straight to the derivative and then simplify. Let's see, g prime. You recognize that this is a sum and difference of several functions, so we just go term by term, taking derivative, okay, and respecting whatever sign you encounter. That's basically what you need to do. Let's go one by one. The first one. What's the derivative of negative x to the 4 over 2? What is that? So that's the same thing, by the way, as negative 1/2 times x to the 4. Yes? Does everybody recognize this? So the negative 1/2 stays there. That's a constant. So derivative of x to the 4.
4x cubed.
So we get 4x cubed. Do you understand this? Okay. Plus the next one. What's the derivative of the next one?
3 times 2x. X squared.
So right here, this 3 comes down times this 3. It gives us a 9, right? So 9x squared. Everybody see that? That's 9x squared. And then derivative minus, what's the derivative of the last term? 2. This is the derivative. Now all we have to do is simplify this, right? Clean this off. So for example, we can simplify the 2 with the 4. 2 in here. So we obtain negative 2x cubed plus 9x squared minus 2. Questions? Do you understand this? Okay. How about the last one? So we have y equals 3x squared minus x plus 1 over x squared. Can we take derivative in this form? Can we use any of the rules that we have at this point? So my question is, do you think that we need to do something to this function before we even try to take derivative? So notice that when you look at it this way, this is a quotient of two functions. We haven't said anything about what to do in this case, right? So all we know is the constant rule, the power rule, but none of that apply here directly, or we have this, sum and difference technique. But here we don't have here a sum or difference. It's happening in the top, but this is a whole fraction. So what you may want to do is, well, okay, I know this one fraction, but I can write this as a bunch of little fractions. Yes? So we can split this into 3 fractions with square root of x in the bottom. Why would this be helpful? Because then we can simplify each of the fractions, because the square root of x, we can bring it to a top as x to a negative 1/2 and then combine. And then you will just have a sum and difference of power expressions, and then use power. Do you understand what I'm saying? You can do that. Or if you don't like to split with fractions, what you can do is bring this guy to a top immediately. It will be multiplying everybody and then distribute them. That's another thing. Bring this as x to a negative 1/2 and then distribute it. Okay? Yeah. Whatever you want. I don't know. I kind of like the splitting part, so that's what I'm going to do. And so to make it more comfortable, I'm going to, instead of square root, I'm going to write x to a 1/2. Okay? So simplifying each term. Remember, when you divide two exponentials with the same base, what do you do with the exponents? You subtract. So 2 minus 1/2. 2 minus 1/2 is 3/2, right? 1.5 is 1 minus 2 minus 0.5 is 1.5, or 1.5, which is 3/2. Okay, so 3 times x to the 3/2, that's the first one. Then minus, what's the next one? Positive 1/2, right? So you have to do 1 minus 1/2. Yes? So x to a 1/2. And the last one? So plus, what's the last one? Just bring it to the top. How do you bring it to the top? We have been doing this all day today. How do you bring this to the top? X to a negative 1/2. Yes? So now we have a function ready. So remember, this is the same thing as the original function, but now this one is in the format that we can apply the rules that we have discussed. Okay? So some of the time, the challenge is, you're given a function and you have to first modify the function in such a way that you can use your rules. Because in many cases, you cannot just use the rules immediately. Okay? Like before, yes, we could just go straight and use the rule. But here, we needed to prepare the problem first. Okay? Keep that in mind. All right, so now that we are here, we can take the derivative. So y prime equals, remember, term by term. What's the derivative of the first one? That's a constant, so it stays there. So derivative of x to a 3/2. 3/2 x. Let's see, let's do it slowly. 3/2 minus 1. Yes? The first one. Then minus the next one. 1/2 x. So the 1/2 minus 1. And the last one would be plus, then negative 1/2 times x to a negative 1/2 minus 1. And literally just applying the power rule in each of them and keeping it like that. Now I'm going to simplify. Do you understand what I just did? Just use the power rule 3 times for each of the expressions. And if there is a constant, you just keep it there because then it will multiply the result. That's a constant multiple. Now let's simplify. All right, so as a 9/2. Now 3/2 minus 1, what is that? 1/2, right? So x to a 1/2, then minus 1/2, x to a negative 1/2, then minus 1/2, x to a negative 3/2. And then let's put this together. So let's see, this is 9 times square root of x over 2.
Wait, where did you get the x to the 1/2 in the beginning? This is in a 3 over 2 minus 1.
What is it?
Oh, okay.
This is
Wow.
Yeah.
So then minus 1 over 2 x to the 1/2 minus 1 over 2 x to the 3/2. And so, I mean, you can stop it right there, but I'm gonna go one more. So this is 9 square root of x over 2 and 1 over 2 square root of x. And okay, this one I'm gonna skip. And if you want, you know, you can combine it and so on, but this is the derivative, so that's fine. But if you want, then, you know, if you want to write as one single expression, then you need to combine this, okay? That's a big fraction. Okay, questions? So taking derivative requires two skills. The first one, of course, is that you need to know the formulas. You need to know the formulas and be able to use them. And the second skill is algebra. What we're doing here is a bunch of algebra. Manipulating things, combining things, move these to the right, to the left, top, down, and that kind of stuff. But you have to make sure that you're comfortable doing this. Okay? So it's algebra and, of course, knowing the rules. If you don't know the rules, then you cannot take the derivative. Questions? All right. So with these basic rules, you can take the derivative of a lot of functions. But there are some functions that we haven't touched on. For example, how about the sine function? What is the derivative of sine? How about the cosine function? What is the derivative of cosine? Okay. And then also, what about when you multiply two functions? What is the derivative of a product? What is the derivative of the quotient of two functions? For example, here, we were able to get away by using the previous rule because we only had a square root of x there. But if I would have done this, and that's it, this plan doesn't work anymore. Because yes, you can still split the three fractions, but you have a plus 1 here in the denominators, and then you will no longer be able to write it in this form. So the power rule is not going to work. So we need to learn what do we do when we have a product of two functions, what do we do when we have a quotient of two functions. There are special rules for those. And like you can probably guess, that's the product rule and the quotient rule. Okay? But we're going to talk about those in, actually I will, I guess, talk about those on Friday, and you will watch it. In the exam, there were a couple of questions that were actually from the Friday's lecture. There were actually two questions in the exam that they were straight from the Friday lecture. The intermediate value theorem question, and the last question in the exam, it was from the Friday lecture. So if you're not watching the lectures, you need to watch them because I'm doing new material in those lectures. Otherwise, you're not going to have time to finish anything in the semester. We cannot do everything that we need to do. 2 days is not enough. We need to have 3 days. Do you understand what I'm saying? Don't ignore Friday's lectures. For example, on Friday lecture, I will do product and quotient rule. Okay, so make sure that you watch it so you understand what they are. Of course, on Monday we'll do a couple of problems, but I expect you to already know the rules by Monday, or at least be familiar with the rules. Okay. All right, but today let's finish with sine and cosine. So let's talk about how do we take the derivative of the sine and cosine functions. And then we're going to do this, and once we discuss the quotient rule, then we'll be able to do the derivative of tangent, cotangent, secant, cosecant. Because those are quotients of, for example, tangent is sine over cosine. So if you know the derivative of sine and derivative of cosine, then you can also take the derivative of the quotient. But you will need to know the quotient rule. Okay? And so the formulas for the other trig functions, they will come in later. Okay. So for this, let me remind you of some special limits. So recall. So let's see, the limit as x approaches 0 of sine of x over x, and limit as x approaches 0 of 1 minus cosine over x. So who remember this? What's the first limit equal to? 1. And the second limit? 0. Good. We're going to use this eventually. Okay? Today. Right now. All right. So remember these limits. So you know the goal here is that we want to figure out what is the derivative of the sine function. we want to figure out what's the derivative of the cosine function. That's what we're going to do. Okay, I'm going to do the sine, and then of course I'll give you the theorem with the result for both, but then the argument for cosine, we're going to leave it to you as a homework because it's very similar. All right, so let's see. Okay, so we want to figure out the derivative of the sine function. All we have right now at our disposal is the definition, because you cannot write this as a sum or a power or something, right? So we cannot use any of the little rules that we know from before. So the only thing now we need to go back to the roots, which is definition. So let's do derivative with respect of x of sine. We know what this is. This is the limit as h approaches 0 of sine of x plus h minus sine of x over h. And then the question is, what do we do here? Let's see, anybody has an idea? Yes?
Use the sign, the sum of angles.
Very good, very good. So here, one thing that we can do is, because by the way, here if you try to multiply by a conjugate, you could try, but that's not going to really get you anywhere. You're going to have this sine square minus that sine square. Really, that's not going to be helpful, okay? And there's not much that we can do here. By the way, there were some strange things that I've been seeing in the exam. But so let me take this opportunity to say, if you have something like this, you have to understand that this guy is in the arguing of the sign. You cannot just move things around outside the sign just because you want to. In other words, you cannot tell me that this is this. Same as, so this is the kind of stuff that you were doing in the exam. You had something like this, and many of you were doing this. Like, take this guy out. Where is that coming from? In fact, sine of 2x, for example, is 2 sine times cosine. Right? If you remember the double angle formula for sine. So this is the argument of the function. So you cannot just take stuff out or something outside, and then if I write this over 2, for example, I'm saying this because I saw this kind of things, and some of you were doing this kind of thing. No, you cannot do that. Okay, you don't have access to the inside of this function. Do you understand what I'm saying? You have to be very careful. So sine of x plus h is not sine of x plus sine of h. There's a formula for that. Like your classmate pointed out, back in trigonometry, you learned how to find the sine of the sum of two angles, right? So let me remind you of that little formula. I guess. Let me increase the recall list. That's one thing that you need to remember. Now, another one that could be a little bit less fresh. I'm going to use alpha and beta. The sine of alpha plus beta, the sum of two angles. What is this? So this is sine of alpha times cosine of beta plus cosine of alpha times sine of beta. Again, that's a formula that you learned back in trigonometry. Okay? Sine cos plus cosine. And if it was a minus, then the same thing, just put a minus in here. Okay? For cosine, because you're going to need it when you do the cosine one, let me just write it down. The cosine of alpha plus beta, the formula is cos sine sine. Okay? So it's cosine of alpha, cosine of beta, and then here is sine of alpha, sine of beta. And the subtlety here is that the sine preserves the symbol, the cosine flips it. So if it's plus, you have to put a minus in here. Okay, and then I guess, let me just tell you, if it's a minus, a minus. If it's a minus here, then it will be a plus in here. Okay, so those are some formulas that you learned back in 3. We're going to need these formulas. For example, here we're going to use the formula for the sine of the sum. Remember, you can think of these things as angles, but they are in gradients. Okay, the sine of the sum. Let's use it. So this becomes limit as h approaches 0. Now the top is sine of x cosine of h plus cosine of x sine of h. Okay, so sine cos plus cos sine. That's the pattern. then minus sine of x over h. Now here we can group some stuff. For example, I can group this guy with this one and factor out a sine. Okay, so let me do that. So this will be the limit as h approaches 0. I'm gonna factor out a sine. In fact, I'm gonna let me factor out a sine. So that will be cosine of h minus 1 over h, and then plus cosine of x plus sine of h over h. Give you a second to see what is happening. So what I did was I put these two guys together, the highlighted ones, factor out the sine, giving me this. Do you see that? Yes? The negative 1 is coming from here when I factor out the sine. And then these other two, cosine times sine of h, they stay like that, and then I broke it as two fractions, each of them over h. Are you okay? All right, now let's take a look at this one. For example, to make this a little bit more familiar, whenever you have a difference, you can always flip it, but what do you need to do? What do you need to do? So a minus b, I want to write it as b minus a. But of course, these two things are not equal. To make them equal, what do I need to do? I put a minus in front. Right? In other words, when you factor out a negative, what you're doing is you're flipping the expression. Do you understand this? And that's what I'm going to do. I want to have a 1 minus cosine. Why? Because that's the form of the special limit that we have in the top. Instead, I could have just factored negative sine, but I guess we wouldn't think about factoring a negative sign, but just a positive sign. So that's why. Now I take out a negative. The reason is because I want to have a 1 minus cosine instead. And then over h, I can just put it here and write as a product. So the over h is on the whole thing, but I can just write negative sign times this over h. Okay? And then this one I can write as cosine times sine of h over h. So we're now ready. So when we take the limit, what happens to this part right here? Remember, the limit is with respect of h. So whatever has an x, that's a constant with respect to this limit. Here, the thing that's changing is h. H is a quantity that's becoming small. X is independent of h. X has nothing to do with h. Do you understand this? This limit is about h, not about x. So this is a constant with respect to the limit. So this part right here is our special limit, becomes 0. And on the other term, what's the limit? Sine of h over h. As h approaches 0, that's 1. So moral of the story, what do we get here? We get negative sine of x times 0 plus cosine times 1. So what is equal to? Cosine. So moral of the story, the derivative of the sine function, what is it? So derivative of sine equals cosine. When you take the derivative, the sine function turns into a cosine function. Questions? So the cosine function carries the information of the slope of the sine function, if you think about it. Okay? All right, so this is one formula, and then you can play the same game. So similarly, we can compute the derivative of the cosine. The proof, I'm gonna leave it to you as a homework. And what you're gonna obtain is negative sine. There's a negative that survives. Okay? So, proof, just do it as a homework. Basically, you use the same idea as before. It's just that you need to use the formula for the cosine of the sum of two angles. And that negative is because, when you use the formula, a minus is going to come up. Okay? Because cos minus sine. So when you start moving things around, that minus will be responsible for, it's responsible for this negative here. So that's a theorem. The derivative of sine is cosine, and the derivative of cosine is negative sine. Okay? Questions? All right, 1 minute. So I guess I'm gonna do 2 examples. So find derivative. For example, now we can do something like 2 times sine, and then we could do something like f of x equals x plus cosine. Let's see, let's find the derivative. So what is y prime here?
2 cosine x.
It will be 2 times cosine of x, applying the constant multiple rule. Keep the 2, and then the derivative of sine is cosine. Yes? And then for the other one, what is f prime? You need to use the sum rule. So what's the derivative of x? 1. The derivative of cosine? Negative sine. So 1 minus sine. Questions? All right. So what's coming now is we talk about product rule. So what do you do when you have a product? What do you do when you have a quotient? That's product rule, quotient rule. What do you do when you have a composition? That's called the chain rule. So what if you have cosine of the square root of x? How do you take the derivative? Or cosine squared? How do you take the derivative? Okay? It's called the chain rule. So those are the things that are coming. I'm going to talk about product and quotient on Friday, and then the other 3 functions, they come from there. I'm going to stop it there, and then on Monday we do chain rule. Okay? That's the plan.